So far, we've looked at examples of collisions in one dimension. In this video, we will look at an example of a collision in two-dimensional space. Consider the following scenario where we have two cars. The first car is driving in a horizontal direction from the right of the screen to the left. It has a mass of 2,500 kilograms and is moving with an initial speed of 25 meters per second. The second car is driving in the vertical direction from the bottom of the screen to the top. It has a mass of 1,500 kilograms and is moving with an initial speed of 20 meters per second. Car 2 is supposed to give way at the intersection, but fails to do so and crashes into the incoming Car 1. The collision is inelastic and causes both cars to deform and join without rebounding. Thus, both cars move off together in the same direction after the collision. Considering the mass and the speed of the two cars, which direction do you think the cars would move along after the collision? Is it paths A, B, C, or D? Let's now apply the law of conservation of momentum to find out exactly which direction they move off in after the collision. We know that Car 1 is moving in the horizontal direction, so there's horizontal momentum there. And we know that Car 2 is moving in the vertical direction, so there's vertical momentum there. This means that there must be both horizontal and vertical momentum immediately after the collision. This rules out paths A and D. The horizontal car has more mass and is also moving with a higher speed, so there's more horizontal momentum than there is vertical momentum. This rules out path C because path C has a larger vertical component than it has a horizontal component. Thus, the most likely path is path B. Now let's calculate the angle. We begin by defining a coordinate system. For convenience, let's call the upward direction as positive y and the direction to the left as positive x. This way, the final velocity will be a positive value in both the x and y directions. We will define the angle with respect to the positive x direction also. Now, the initial momentum of Car 1 is equal to the product of its mass and its initial velocity, which comes to 62,500 kilograms meters per second. The initial momentum of Car 2 is equal to the product of its mass and its initial velocity, which comes to 30,000 kilograms meters per second. Vectorially, the momentum of Car 1 is represented by the horizontal arrow, and the momentum of Car 2 is represented by the vertical arrow. Since momentum is conserved, then the vector sum of the initial momenta must be equal to the final momentum. P' is thus the vector sum of the two arrows P1 and P2. Since they are right angles to each other, then the final momentum, P', is the hypotenuse of the right-angled triangle that P1 and P2 makes up. So what then is the magnitude of P' equal to? That is, what is the value of the final momentum? The magnitude of P' is found by using Pythagoras' theorem to give 69,300 kilograms meters per second. The angle can be found by using the tan function, where tan theta is equal to P2 over P1. Taking the inverse of tan gives us an angle of 26 degrees. So the final momentum of the two cars after the collision is 69,300 kilograms meters per second, directed at an angle of 26 degrees above the positive x direction. Now let's try the algebraic method. Let's start with the horizontal x direction. The total momentum before is equal to the total momentum after. Since Car 2 is moving vertically, it has no component of momentum in the x direction, so P2 in the x direction is 0. Now the initial momentum of Car 1 is its mass times its initial velocity. The final momentum will be the combined mass of the two cars as they are stuck together, multiplied by the x component of the final velocity. Of course, the x component of the final velocity is the cosine of the final velocity. In this equation, we know the masses of the two cars and the initial velocity of Car 1, but we don't know the final velocity or the angle, so we can't proceed as there are two unknown parameters in this equation. Now let's have a look in the vertical y direction. The total momentum before is equal to the total momentum after. Since car 1 is moving horizontally, it has no vertical momentum in the y direction, so P1y is 0. Now the initial momentum of car 2 is its mass times its initial velocity. The final momentum will be the combined mass of the two cars as they're stuck together multiplied by the y component of the final velocity. Of course, the y component of the final velocity is the sine of the final velocity. In this equation, we know the masses and the initial velocity of car 2, but we don't know the final velocity or the angle, so we can't proceed as there are two unknown parameters in this equation. But we now have two equations with the same two unknown variables, so we can use simultaneous equations to solve them. Let's clear the screen a little bit so that we've got some space to solve the equations. We can use simultaneous equations to solve for either v prime, or the final velocity, or theta first. But looking at the two equations, we can see that there's a sine theta in one and a cos theta in the other. If we take the ratio of sine theta over cos theta, we get tan theta. We also notice that m1 plus m2 and v prime cancel out as well. So we end up with a simple formula of the ratio of the initial vertical momentum over the initial horizontal momentum being equal to tan theta. Transposing for the angle gives us the following equation. We can now substitute in our values to solve for theta, and this gives us a value of 26 degrees, the same as when we solved it using the vector method. Now that we have the angle, we can substitute the angle into any one of our one-dimensional momentum equations to solve for the final velocity v prime. Let's use the first equation. Transposing for v prime from the first equation gives us m1 v1 divided by the sum of the masses and cos theta. We can now substitute in the values to solve for v prime. So what is the value of v prime? That is, what is the final speed of the two cars? Solving for v prime gives us a value of 17.4 meters per second. That is, both cars travel with a speed of 17.4 meters per second at an angle of 26 degrees above the positive x-axis after the collision. As a final note, when dealing with two-dimensional problems, remember to resolve the momentum of each object into its two dimensions and treat the conservation momentum in each dimension separately.